Hi, welcome to this session on conformal lattices. In the last session, we have learned how to create box grid lattices for a given part. We have observed that in the first place, we have created the box grid for the bounding box of the given part, and later it is trimmed to fit the body. Sometimes it is possible that some of these lattice curves are not fit properly. There can be loose beams. Of course, this could be addressed by trimming the grid like we did, or post-process the extracted curves and remove the undesired ones. On the other hand, conformal lattices are the ones that fit to the geometry and the skin follows the surface of the geometry. This is not only good aesthetically but also desired mechanically. The main requirement is that the given solid part should be closed. A simple check can be that the volume of the part should be positive. If there is a mesh and it is converted into a solid body, sometimes it can have multiple faces and this would affect the performance. These are some of the things to keep in mind. So in this session, we will learn how to create a regular conformal lattice structure and learn how to also create stochastic Voronoi lattice. This is an organic and conformal to the given part that can be controlled by the size and density of the cells. Please open the file Conformal Lattices Starter. The first step is to import the geometries for which we want to create the lattice structure. So in this case, we have two different versions of the geometry. The piston, which looks like this, the design space and the non-design space. And we have the suspension arm, the design space and the non-design space. So the design space is something which will be filled with the lattices and the non-design space will remain the same. So here we made a filter to select between different geometry types, and based on that we get the design space and the non-design space. One can also import externally created CAD geometries using the components, import geometry, parasolid, step, CATIA and so on. So let's move to the next step to create the lattice skeleton. So here we have the design space and we have a simple logic here to construct the bounding box of the part, as you can see, and based on the bounding box we deconstruct it such that we get the dimensions of the part in X, Y and Z directions. So we divide those dimensions by the number of cells which are desired for us. So in this case we want 10 cells in X and Y directions and 6 cells in the Z direction. So feel free to change these values based on the requirement. And here we make the round, that means the integer values. Here we have the size of the cell in X, Y and Z directions. So now we can use this component from conformal subcategory inside Mocha, a regular lattice region. And here we can define the X size, Y size and the Z size. That means the size of the cell in each directions. So this creates a regular conformal lattice for the given body. Here we can define the body and then this will create the region first. So here there are also a couple of other inputs. In the type we can select between different cells that we want to create. So here we have 4 different types. And in the orientation we can define a custom orientation of the cell based on the requirement. So here we will have to define a rotation transformation matrix with reference to the XY plane. So how can we define that? We can open this example file and here we have a simple example how to extract the transformation matrix. So here we have a point and we are rotating with reference to an axis, and with this component we can get a transformation matrix, and this can be given as an input for orientation. So now we have created a regular conformal lattice region. So in the next step we will have to extract the curves. So we can do that by using this component conformal lattice from regions, where we will define the region that we have created and the container, which is our design space. We can see that the lattice curves are now extracted, so we can hide all the other parts in the viewer and visualize only the lattice curves. So we can observe that these are conformal to the given geometry, and here we can also see that these are the regular conformal lattice region. So now we have the curves And in the next step, we will make some post-processing of these curves such that no curves exist in the non-design space. So we can do that by evaluating these curves at a parameter 0.5, which would give us the midpoints of the curves, and then we can check if these points are in the non-design space. So here we get a boolean output which is true or false, and we can use this boolean output and filter out the curves which are not in the non-design space like this. And we can visualize the non-design space. So here we can see that none of the curves are in the non-design space. So let's move to the next step to define the radius of the curves in order to create the volumes. So here we can define the radius of the curves using two different approaches. One is to have the constant radius for the whole lattice skeleton. We can do that by using this component, construct pipe curve, and then define the radius here like this. So this will create the pipe curves with this defined radius, which is constant for the whole lattice skeleton. And later in the next step we will see how to convert them into volumes. We can also do it in a slightly different way by defining a field. Imagine having a constant radius of the lattice beams in the design space, and when they are transitioning to the non-design regions, we would need to have a larger radius. So how can we do that? We can define a local field for the non-design space using this component, local field. Here we can define the radius of the beam at the non-design regions. So in this case, we will define a value of 0.8 millimeters of the beam radius. And here there are also a couple of other inputs on the field component, which is the radius of the field. And then here we can also define the transition distance. That means how does the field transition from this value to a global value. So here we have a global value. Using this component we can define 0.4 as the global value. So that means 0.4 is the radius of the beams in the design space, and at the non-design regions it would be 0.8. So with this field we can use the component beam evaluate field, which is this one, and then here we can use the lattice curves that we have extracted before, and here we can define a resolution. That means the number of points on the curve at which this field will be evaluated. So we can visualize the pipe curves in the viewer. So as you can see, the curves have more radius in the non-design regions as we have desired, and when it is slowly transitioning to the design space, the radius is constant, which is 0.4. So we can better visualize that by viewing also the non-design space. So here now we can see them better. So now we have the pipe curves with the defined radius. So in the next step we will convert them into volumes. So we can hide this non-design space and the pipe curves and move to the next step, converting beams to volumes. So here we can connect this cable so that we have the pipe curves. Now we move from Mocha to Dendrise. So in Mocha we have created the lattice skeleton. That means we have extracted the curves. In the next stage, now we have to convert them into volume. So this is where we will use Dendrise and the respective components. So here we have a couple of components which are used at different stages. The first one that we will use is converting the pipe curves to volume. So here we can use this component, pipe curves to volume. And here, as you observe, there is also another input to define the settings. So these settings define the voxel size and the other parameters. We can do that by using this component create settings, and here we can define the voxel size. So please remember that the voxel size should be at least 33% of the pipe radius in order to accurately represent the circular cross section. So we can use these settings now. So we can see that the lattice beams are created now. So as we have desired, the radius is more at the non-design spaces and smoothly transitioned like this. So now we have created the lattice for the design space, and in the next step we will have to combine this with the non-design space. These volumes can also be exported as .vdb file. So here we can use this component export volume and use the extension .vdb to export these volumes, and in a similar way we can import these volumes using the other component import volume. So now we have the beam volumes and the dendrise settings for creating the volumes, and in the next step we have to make a Boolean union of this lattice structure with the non-design space. So here we have the design space and the non-design space. So why do we have the design space again? Here we can make like a intersection between the lattice volume and the design space such that none of the beams are outside the design space. So here the design space is a solid body, so we can convert this into a mesh using this component body to mesh, and one can define the other parameters of this component such as max edge, min edge and the tolerances to accurately represent the design space, and then convert the mesh to volume using this component, and here we have to define the dendrise settings. So now we have the volume of the design space, which looks nice, and then in the next step we make a intersection using the component volume intersection between the beams and the design space. So now we have the beams which are only in the design space, so we can verify that by visualizing the design space, and here we can see that all the beams are inside the design space. And now we can create the volume for the non-design space using the same approach by just switching the cable, and here we have the volume of the non-design space. So we can make a Boolean union of this together using the component volume union, and here we have achieved the final lattice structure, which is a volume. So this volume can also be converted into a mesh using this component volume to mesh, and the final mesh can be exported as a STL file with the defined name as .stl extension. Now we can go to the first step where we have imported the design and the non-design space, which are these ones, and as we have developed a parametric and algorithmically driven workflow to create these conformal lattice structures for a defined body, so we can simply switch between different geometries and observe that how it runs automatically with each step. So as we have observed, we have now the lattice structure for a different geometry, which is suspension arm. So this is how we create regular conformal lattices. So if you go to the second stage where we are creating the lattice skeleton, we are using this component regular lattice region. So one can also use other components which are density lattice region, and here we will define the density of the seats. That means how many points do we need for unit volume. So please also check out this example file to learn how to set up this workflow using the density lattice. And one can also switch between different lattice cell types and observe that how the workflow runs automatically. This is the end of this session and the course for the lattice structures. I hope you enjoyed it.